Hi, and welcome back to Dynamic Programming and Structural Econometrics. This time it's virtual. So it's lecture 4 and a direct continuation of what we did in lecture 3 on numerical integration for one-dimensional problems. We already know a little bit about Quadrature and how to do Monte Carlo. We covered all the different rules, or many of the different rules in Kinjit's textbook. You know, Gauss Legendre, that's very powerful. You want to integrate something on bounded support. And if you're Gauss Hermite, if you want to do something that looks like normally distributed variables with unbounded support, and the Gauss Grid that has support from 0 to infinity. Very good for calculating discounted value of infinite sums in continuous time, and the Gauss-Chebyshev for the constant nodes and so on. We know all about the error analysis in this 1D dimension thing. Very, very straightforward. So we're going to look at how that extends to multidimensional integration now. And we're going to start with something called the product rule, but you'll see that in just a second. So this lecture is mostly about how this extends to multidimensional integration, and we're going to look at integrals on the form, on this form here. So that is an integral of a function, or maybe a product of two functions, f and g, which are both functions of several variables, x1 up to xt. So, for example, think about our think about Dietzsch's model with extended with another income shock, or the consumption savings model where you both have income shocks and stochastic interest rates. There you would need to take expectations with respect to two stochastic variables. In that case, well, the integral of interest really looks like this, because it's an integral of the value function or utility function, a static problem, weighted with the density of the support, the density of the stochastic variables x1 to xt, in that case the interest rate and the income shock, and then integrated over the support of those distributions. So that's an example. So it doesn't have so that's the kind of problems we look at. Okay, it doesn't have to be only two variables. These ideas extend to high dimensional integrals. So anyway, what we're going to talk about is how do you solve this problem. First, with Quadrature, the natural extension here is using the so-called product rule. It turns out to be a subpicture cursor dimensionality. I'll explain that in a second. The problem here, the cursor dimensionality, is really that the number of required Quadrature nodes is to obtain a level given degree of approximation for a given dimension of the integral is just increasing exponentially in the dimension of the problem. So it increases exponentially in D. So that's a motivation for doing Monte Carlo that just effectively breaks that cursor dimensionality. Now, there's a trade-off here, because actually Quadrature can be really, really powerful for solving small and moderate-sized problems, and really nail integrals of size 1, 2, 3, something like that. But once you go to very high dimensional integrals, like a 50-dimensional or 100-dimensional integral, well, that cursor dimensionality is really going to kick you. Okay, so in order to do Monte Carlo, we need to be able to sample from the distributions of this x. So if it's kind of, it's G here, that's like the density, we'd be able to sample from the distribution capital G, this CDF of all these x1s up to xd. If you're able to sample from that, we just put them into the function and average the results, and that converges to that integral. That's the idea. So in order to even start talking about how to do Monte Carlo, we need to be able to sample from multivariate distributions. And we're going to take the example of a normal and a log normal and show how to do that. So these are simple distributions to sample from. So, but of course, if you want to say sample from some truncated distribution or some distribution where you can't do the tricks I'm showing you, you have to look up and study on your own. But I'm showing you here for the normal and the log normal. And for other distributions where you were able to make the transformation from uniform random draws to the distribution of interest easily. Okay, so once you do that, then once you start to do Monte Carlo, you need to get some random draws, and they can be random, but the randomness also creates randomness in the result. And sometimes you can get unlucky to get like some random draws that just randomly ended in one side of the distribution, and then you get a biased result, right? And so there's ways to avoid that or reduce that finite sample bias, or you can say this the variance of the estimates, reduce that variance that you get on your estimate by using various reduction techniques. So other types of draws like Halton draws and Sobel draws that is able to reduce variance, so you don't need to take so many draws. There are some issues with dependency of some of these random grids in high dimensions, and I'll compare these different types of draws. In particular, Halton draws have some issues, and then what people do is they kind of shuffle them around to avoid that dependency that you don't really want. Anyway, it's going to be very clear when you see the pictures. And then I'll do what I can to try to illustrate that Monte Carlo really breaks the curse of dimensionality, illustrate that you got root inconsistency, and that root inconsistency, rate of convergence, not even depending on the size of the integral, so that sense it breaks the curse of dimensionality. And then I'm going to compare Monte Carlo with also sparse grids for some test problems, and generally compare the different methods that we go through for varying dimensionality. Now, on GitHub, there's actually a little application of portfolio choice model. So here in this talk, I'm going to go straight to the integral, work with very simple test problems like taking what is the mean in calculating what is the mean of a log normal or product of log normal distributions that potentially allow for some correlation, simple test problems. But if you want to do some more economics, you may want to check out the application of a portfolio choice model that is on GitHub, which is trying to mimic the example that Ken Judd has in his textbook, where you have a model where some investor choose between placing his assets between, say, like k different assets that has stochastic returns, and then you want to calculate what is the expected utility of a given portfolio, given that he's so and so little risk averse or so much risk averse, and what is the optimal portfolio weights, how much should I put on each of these different assets, depending on what the distribution of the asset returns are. If it's a very safe asset, if asset returns are very correlated, mutually correlated, should I invest more or less, and so on. So that's a little application there. It's not a dynamic model because we haven't had, didn't talk about functional approximation, how to solve high dimensional dynamic programming yet. So they're trying to boil it down just to the static problems to work only with dealing with the integral. And then next week we're going to talk about functional approximation and high dimensional dynamic programming. So that's kind of the plan. So like I said, we can start with multidimensional quadrature, and so generally you can say it's more complicated because the simple methods here are subject to recursive dimensionality, and you can see it actually directly from this formula here. This is a product rule for the generic product rule for quadrature. And of course, then depending on the quadrature method, you would have different nodes and different weights, and you would have to, adjust them differently to fit to your problem by appropriate change of variables and so on. But really what it is that it is, just a nested computation of a series of integrals, okay, using the same formula. So if you have a two-dimensional problem, well, for each of the quadrature nodes, in one dimension, you calculate the integral for using a number of quadrature nodes in the other dimension, okay? And that gives rise to all the different combinations of quadrature nodes. You see here, of course, f is a function in several variables, 1 up to d, right? But then if you want to calculate using this nesting way of calculating the integral, then what you need is all the combinations of the nodes in dimension 1 and the nodes in dimension 2 and the corresponding weights multiplied to each other, because that's what you get, right? If you were doing what I kind of just suggested, and then you add the whole thing up, and that results in this like a double sum, if it's two-dimensional, triple sum, this is three-dimensional, and you can kind of see we can see where we're going, right? And so what are the number of elements in the sum? Well, that's n to the power of the number of dimensions, right? Because it's how many elements it's going to be in the sum. So this is why it extends naturally, but it also extends computationally in an exponentially increasing way. So here the problem here is just a little detail. The problem is really we're making an integral over the d-dimensional integral where the you can see the end bounds on the intervals in each of the dimensions is the same a and b for all the dimensions. Doesn't have to be like that. I mean, you could have a1, a2, a3 all the way up to ad. And same for the b's, and then you would just have to like take all the combinations. So it doesn't have to be the same intervals for all the different variables, not at all. Okay, and that's like a trivial change here. And also here, the number of nodes are assumed to be the same. Doesn't have to be like that. You can put a little subscript n here and a little subscript 1 here, and then that would already be pretty general, right? So you can have different number of nodes in different different dimensions easily, and then the product rule just extends. Okay, so you can easily do that. So this is so you can say here we will left with something that is potentially high dimensional subject to recursive dimensionality, because the product rule here is based on Gaussian quadrature, like the full tensor product of orthogonal polynomials of whatever polynomial basis you're based on. If it's like Hermite quadrature, it's Hermite polynomials. And so that is that's computationally intensive. It's especially a high dimensional integral. Here just for illustration, let's just compute what would the required number of grid points be for numbers or nodes and weights be for various dimensional integrals. So here we're doing like 1 up to 10, and then 20, 30, and 50. And you see if you have like 10 nodes in each of the dimensions, if you thought, okay, I need 10 nodes to get like a good approximation of my integral in each of these dimensions, well, then it kind of explodes, 10 to the power of 50, that's just, infeasible to share and store in your computer, right? So and it stops way before that. And, you may ask, who says we really need to, 10 quadrature nodes in each dimension? What if 2 is enough? We get a very good approximation of something that is if the function could be approximated by a polynomial of 2 to the power of 2 times n, that's 4 in our case, minus 1, like a third order polynomial. Maybe we could do with 2, but even with 2, right? Look at what's going on. I mean, eventually you're going to be hit by the recursive dimensionality. So if your function just need 2 points, right? Then even just a 30-dimensional integral becomes like billions of quadrature points that you need. Okay, so that's pretty nasty. Let's pull it back here. And so what else can we do? Let's go back a slide. Then there is also other ways to do quadrature. It's based on Smoljac's algorithm that uses sparse grids. So the benefit of Smoljac's algorithm is that the number of required grid points to obtain a given level of approximation is not increasing in the same exponential way. Okay, so it's definitely increasing in the number of dimensions, but it's not increasing in the same exponential ways, increasing polynomially. So that is not, there's still a recursive dimensionality, but it's not a recursive dimensionality in an exponential sense. It's just you still would have problem solving very high dimensional integrals with Smoljak grids. And therefore, there's the Monte Carlo integration really breaks that recursive dimensionality here. It's not only just increasing in polynomially, it's just completely independent of the dimension. Our ability to approximate the integral, the rate of conversions, the rate at which the variance on our estimate is decreasing is 1 over the square root of n. You get the usual parametric rate that you know from your statistics, and that just applies to this integral out of the box, doesn't depend on d. So that's really powerful and really good for high dimensional integration. I'm not saying you want to do Monte Carlo all the time. That's going to be very clear once you see it. But let's first talk about how to do it, and then we'll see. Okay, so here's Monte Carlo. So we're looking at we could use Monte Carlo to compute multidimensional definite integral in this form. which is the integral of f of x times g of x integrated or with respect to x over the support of this particular distribution g. Okay. Now, it doesn't have to be, this distribution here, that could just be the uniform distribution if you're looking for the integral of just some function that does not necessarily is a function of stochastic variables. So you can just still use, in that case, then the integral just collapses to this, and then you would be like, for example, integrating on the uniform hypercube, and you would make like a change of variable to make it adapt to your problem and so on. Okay, now, okay, so but what this really is here, what is that? That is the definition of the expected value of a function of a stochastic variable that has distribution capital G and density little g, okay, and that has this support with this support omega. It's just the expectation of that function, okay. So how do you usually estimate expectations? Well, we have a very, very simple estimator for the expectation. It's a sample average. So the sample average, we know that that converges. It's a consistent estimator for the mean, right? So we can just take a sample average if we have a sample. So what do we do is we create a sample because we know the distribution of x, right? So we know the density. We can just take a sample of n points, or n vectors, because x is a vector, right? N vectors from the distribution of x, and then it calculates just the sample average of the function. Okay, so we calculate here the sample average of the function evaluated at all these different, n samples or n sample points. Okay, and that is a good approximation. N go to infinity, then that sample average is converging to the mean as n go to infinity, and that is what the law of large numbers gives us. So under weak regularity conditions, blah blah blah. But the law of large numbers, if you have a random sample from G, essentially says that the limit as n go to infinity is equal to the average, is the expected value of the function, which is the integral of interest, because that's what we just said, right? This expectation is equal to the integral we're interested in solving. Now you don't only get consistency, that is, as n go to infinity, you're going to nail it. You also get asymptotic normality, which is allowing us to do inference on our approximation of the integral. So by the central limit theorem, we would have that if you take our estimate, this is just a sample average, just call it Qn to emphasize it's a function of n. It depends on the number of observations. It's really what we have here, right? This our estimate, or a sample average, our Monte Carlo estimate. And subtract the true integral, which is its expectation, multiply with root n, then that is converging in distribution. This is what this is, okay? Converging in distribution to a normal with a mean 0. In other words, these two must be close to each other, right? And a constant variance. So if you multiply with root n, you get a constant variance. And what I mean by constant, it doesn't depend on n, okay? It's just converging to the same distribution, this normal distribution, as n go to infinity. For every value, then you're gonna end up in the same distribution. Now, if this is not, if this does not depend on n, well, what does it imply for our standard error on the mean? Well, the standard error on the mean is this the square root of sigma squared, so the sigma divided by the square root of n. So that goes to 0 by a rate which is 1 over the square root of n. And notice here, this is the power of Monte Carlo. This, you call it the parametric rate. That does not depend on the dimension of x. Not at all. There's no d. Okay, it doesn't depend on d. It doesn't depend on it. You get the same consistency, the same rate of convergence, irrespectively of how big your integral is. Now that is really, really powerful, and that is the huge advantage of Monte Carlo compared to multideterministic methods, that it uses the randomization to break that curse of dimensionality, and so compared to, for example, Quadrature, where there were higher number of nodes would depend on the dimension, which in fact increase exponentially if you use the product rule. Well, then then this is much better, right? It's at least for very high dimensional. Of course, you're still going to get variance, right? Still going to get a variance, and that variance is not zero. So this means that there's some approximation error, if you will. I'm waving my hand, but some variance on that estimate that could be big. Okay, and we'll see that in some simulations in just a minute. Okay, but okay, so in order to even do Monte Carlo, we would need to be able to have a sample. And it has to be the sample from the distribution of x. So depending on what that distribution is, you need to be able to sample from. But let's just start simple. We start first simple with, do one dimension. Then try to see if we can get some uniform random numbers. We want to transform those uniform random numbers to the distribution of interest. Then we can try to see, okay, now if it's a multi-dimensional distribution, how do we deal with that? Okay, and then we go from there. But so all of this starts with a random number generator. Okay, and so here's some ways to get random numbers in Python. You can get like this basic functionality, just return a scalar random number. It's called random. That's like intrinsic in Python. So that's there. But NumPy has like a nice vectorized version of it. You can get uniform random numbers. It's actually many distributions. You can just draw directly from a log normal if you want, or normal distribution, or whatever distribution is implemented in NumPy. You would have to go like look up in the documentation to figure out what you can get out of that. Usually, most of these are like one-dimensional distributions, and you would have to like scale it up or specify what the variance covariance matrix would be if you go to multi-dimension. And then SciPy stats, that gives nice functions for probability density functions, or inverse probability density functions, or the inverse CDFs and the CDF function. All these statistical functions that you need is in SciPy stats, so you might want to look at that. And then there's a chaos pi, which is what we're going to use actually for some of the stuff we're doing, because it allows us also to do not only ordinary Monte Carlo with random numbers, but also a quasi Monte Carlo using Halton sequences instead of random numbers, and Sobol sequences and random numbers instead of random numbers. And it can also use a whole other sets of grids, like just a regular grid and Chebyshev grids and Chebyshev nodes and Quadrature nodes for Gauss-Ligueur and Gauss-Hermite. All this stuff you can get out of KSPy. It's actually a pretty nice and broad package that's at least I found pretty useful. I don't know how many other people are using it, but it did the job for this lecture. Okay, so here's an installation of that. So it's not like a standard package, so you have to pip install it, and here's the command. And so here, let's do that. So I'm just reading all those libraries. And so, by the way, you can just, if you don't have KSPy, just uncomment this line and you will get it. The exclamation mark makes you go to terminal directly, and then it just sets this command there, the pip install command there, and then it's going to install it for you, hopefully. Otherwise, go to the website, figure out how to install it, and then go from there. So for me, it tells me, well, you already installed it, so you don't need to install it. So I'm going to uncomment this again. Okay, and then we need a little nice function to just plot some distribution. It allows us to make a little histogram of the data, and then also plot, if you want a theoretical distribution, a theoretical distribution of the integral. You can also I think also you can say you want to look at the CDF instead, and it kind of accumulates instead. But that's different ways to let's not spend time on that and just move on and do it. Look at it. So here's what we're doing. We're starting simple, generating a sample of 100 observations, 100 Monte Carlo samples, drawing just from the uniform random distribution. In NumPy, we're taking uniform random numbers. Okay, so that is what is in X. So X is here. Well, let's just print the X. So you see a bunch of numbers, and it's all there. These are numbers between 0 and 1, and they're kind of random. Okay, and then we can do our histogram here and plot them. And so that's what we're doing here. So now we are plotting a histogram. I mean, based on 100 observations, it's probably not wise to reject that this could be a uniform distribution. But it does not look like it's definitely not density is not equal to 1 everywhere, right? But this is just because it's a finite sample. And so that's the first thing to realize when you do simulation, right? Things, they change all the time, right? You get new random numbers every time, and this picture is going to be looking different, okay? But on average, it's going to be a uniform distribution. And if you take more distributions, you get more Monte Carlo draws, you get less variance. It changes less from period, from execution to execution. And it do like 10,000. It starts to look more and more like the uniform. And let's do I don't know how many that was, but that was definitely a lot. My glasses, I need my glasses, probably 1 million, right? So that really nails it, right? And so if you would, so let's see, what would the integral from 0 to 1 on this distribution be? I mean, that's really easy, right? It's what is the range? It's 0 to 1, and it's just 1 everywhere, right? So you should then remember to do the adjustment with the change of variable, so you get half the weights and so on. So I predict the variance is, or the average number is going to be 1/2, right? That's the average here, which is the integral multiplied by x, the value down here on this interval. So what is that? Let's just compute it. It's NP mean, right? That's how we do Monte Carlo, NP mean. So what does it print out? Exactly 1/2. And of course, your Monte Carlo estimate is going to, it's going to vary more if you have few observations. So you only have 10. Well, it's not exactly half. It's kind of in the ballpark, right? But you see here, it changes every time, and it's a lot of variance. But if I increase the number of observations, well, I get closer and closer. And that rate at which it gets closer is the variance, or the standard deviation is reduced by a rate of 1/√n. So that is pretty, that looks like, we're going to illustrate it more clearly later, but that looks like variance is definitely increasing or decreasing in the number of observations. And it also looks like if you go from this amount to to this amount, then the change is going to be less and less, right? So it makes sense that it decreases with something like a √n. Anyway, that's very simple. So let's start with that. Of course, you don't have to work with uniform. You can work with other types of distribution, and then you would just replace here whatever the distribution would be that you're taking random numbers from. It could be a log normal, exponential. It could be the normal distribution. It could be the Fisher's, chi-square, Gumbel distributions, geometric distribution. It doesn't even have to be a continuous distribution. You can have whatever distribution you can sample from, and then you calculate the expectation of a function of that random variable with respect to that distribution that that random variable is coming from. There's a bunch of there's some links here to documentation in SciPy and KSPy that you may want to look at to discover the opportunities. Okay, so here's a simulation from a log null. Okay, so I'm doing it twice. We're doing it both for a very small sample, for a bigger sample, and you see, well, there is a bigger chance of getting draws here where the probability is high, and a lot smaller chance for getting it out here, right? It was only like a couple of draws here. So we only had 10. I think this is just one draw. But we didn't get anyone next to it. So that of course, then you take more and more draws, you get a better coverage of the integral. If you were to do Monte Carlo, well, then you would just say print the NP mean of xsim here in this case, and then it would print out what those are, and it's going to be 1.65 or something, because I think the mean of the log normal distribution with these parameters is around that. I think it's something like, what is it? It's like mu, which is 0 plus the standard, this guy here divided by 2, and then you take the exponential, something like that. Okay, anyway, it's nailing it, and you get closer and closer to it, okay, as you get more and more observations. That's kind of the logic, okay? Anyway, so that's Monte Carlo, and you get new results every time. But we know how to. This is simple. You just get simple simple ways to draw from a one-dimensional distribution. So, but how do we sample from other distributions if they're not in Python? Okay, then the cool thing is you can just, if you just have a random number generator for a uniform distribution, okay, then you can just transform these to become whatever distribution you have the inverse distribution of. And sometimes if you write your code in C, or you don't have, you know, all these libraries, or, you know, you write some other language, you may have a random number generator just for the uniform random numbers, but then you can still code up and just by simple transformations get the log normal and normal and the Fisher and everything is just have the inverse of that distribution. So here's how you do that. So you sample based on uniform random numbers, and let's just say, okay, now f, it's not the function, but it's the CDF of the random variable of interest. Then you can transform, you know, go from the quantiles of that distribution to x itself by taking the inverse. Okay, so because, you know, q would be equal to f of capital F of x, so you can take the inverse of that to, if you have the quantiles. But quantiles lives on the interval 0, 1, 1. So what you do is you simulate a bunch of random numbers from a standard uniform distribution limited between 0 and 1. These are your quantiles. Put them into the inverse of the distribution of the CDFs, or the inverse of the distribution of the distribution of interest. And then what you get out is actually distributed according to F. Okay, and that is, you can see it pretty clearly here in this picture. You got basically, here you got some CDF, okay, that's F, okay, and then you got the inverse, which kind of just mirrored in the 45-degree line, right? It's like switching the axis of the function, right? So, you know, y values become x values and vice versa, okay? And so what you then do is you essentially, you take a uniform random number between 0 and 1, okay? Look up in the inverse, say I got this number here, then it's my x value here, right? So, and here it looks like the median, you know, this is around 0.5. The median, this distribution is is 0. So, but if you go further out, you have to go further up. And this guy here is continuing all the way up here in the tail. So the variance is very big. Well, then you're going to get very big numbers out here with, you get, you know, you get more variance in the distribution. All right, so that's a way to do the inverse transformation sampling. You just, you know, stick the uniform random numbers into the inverse of the distribution, and then you move on. Here's some examples. You got the normal distribution, looks like this. This is a CDF of the standard normal. So you have your normal distributed variable here minus its mean divided by its standard deviation. Now you got something that's standard normal distributed that returns a quantile. Okay, so that is returning the quantiles in the distributions of the standard normal of the normal distributed variable with mean, mu, and sigma. So that's it. Now this can be just inverted, right? So if you're interested in we're interested in getting x, right? So we just invert that, and then we get mu plus sigma times the inverse of the CDF of the standard normal, and then you evaluate that at the uniform random numbers. Okay, and then, you know, for the log normal distribution, it's really the log of x that's normally distributed. So, and you can also make that transformation so that now you just need to take the exponential, which you did to get the log normally distributed variables. And here's the one for the log normal distribution at this CDF, and you can invert that as well. And there's, you know, Python has all these different you know, functions that implements all these inverse CDFs, and I think they usually have the extensions called PPF, right? Yeah. Anyway, it's not in NumPy; it is in SciPy. Right? So here's an example. Let's just do a simple one-dimensional example. So we're gonna make a little function that does some log normal distributed variables. What we start doing is we start drawing the uniform random numbers, and then we transform them using the formula we just had here. This is the formula for the inverse of the log normal distribution with the parameters mu and sigma that determines the corresponding mean and standard deviation in the log of the log of the exponent, or the log of the random variable. And so that is really just what we're doing here. And here's the non-PPF that's inverse of the standard normal CDF. And then we just scale them up by sigma to get the variance sigma squared. We add mu to get the mean mu instead of 0. We take the exponential to make the normally distributed variables to log normal, then we're done. Okay, so that's really just inverse transformation sampling of something that starts to be uniform and comes out to be normal. And we can actually, I'm here I'm plotting the histogram. You see, it doesn't really look like a log normal distribution. And we can also like plot it together with, instead of plotting, well, no, let's not do that. Let's just move on. Okay, and this is, in some sense, this is trivial, right? But now you can see, at least you can see how it's transforming that distribution. I mean, we could, of course, just have X equal to those. You'd see they do not at all look like a uniform, log normal distribution. They look like the uniform, but this is mapped into that distribution once we make the transformation. So that's that. Then you end up with this, right? This is what is going on in this line here. So very, very, very simple way to simulate draws, and we're going to use that idea and extend it once we go to multidimensional integration. Before we go there, I really want to say a little bit about how do you repeat the talk about how you repeat simulations. And so, and what happens, you see, when I call this function, let's crack down this a little bit, you see the distribution changes every time, right? But if I'm trying to solve, like a dynamic programming problem by backward induction, okay, or by successive approximation of fixed point iterations, and I want my algorithm to converge, and then inside that algorithm, I'm calculating an integral using Monte Carlo, but then I use new draws every time. Well, how is that ever going to converge? Because now the integral is stochastic, and so for every iteration I'm doing, I get a new integral. And so if I want this to converge to machine precision, to really nail the fixed point of the Bellman equation, well, it's just never going to converge because you get new draws every time. So that's why you want to sometimes fix the sequence of draws to use the same over and over again. Otherwise, if the integral is changing over time, the algorithm is not going to converge. Just the same thing you need to do. You need to do the same thing in the portfolio example that we have on GitHub. Right here, you're just maximizing the expected utility, which involves calculating an integral over a bunch of different random numbers or random returns. Right? If you do that by Monte Carlo, then as you search over the portfolio weights, the weights of each of these different assets that you have in your portfolio, well, your Newton algorithm, how is that ever going to converge if every time you make a step with your Newton algorithm, you look at a new portfolio, or you need a new set of asset returns and expected utility of that portfolio. So that's why it's really important to think about where do you fix the C when you do use Monte Carlo within other algorithms. Okay, so here's a little trivial example of that, and that is that's for the log normal again. And now you see here what I'm doing is I'm doing the same thing twice. I'm taking some stuff from the log normal distribution, 50 draws, and then I'm just repeating that graph twice, and you see I get different numbers. Okay, I mean, this is not surprising, but this is what because I draw from the random number generator twice. Okay, now imagine this was done inside your loop. We're trying to calculate get some mean that had to converge. Well, you would never be able to converge. I would want to have the same numbers in the graphs every time. But there's a way out. What you can do is you can get the state of the random number generator, save it inside a variable. That is fixed. Okay, it's going to be a new state every time you call the program, but you can then fix the state within the loop simply just by, say, uncommenting this guy here. That is set the same. Then it sets the state of the random number generator to be the same every time the loop is executed, and all of a sudden you see these pictures are the same, right? So of course it matters where you do that. You could also have just moved this outside the loop, and then it would not only be that's not what I want to do. No, what I want to do is you can also just fix this state to something fixed so that it's the same all the time. Like, for example, setting the random seed to some number. Okay, now you see here, now the number is the same every time, right? I get the same histogram no matter when I call it. But if I were to do like this and let the state update every time, I get a new distribution every time I call the program. Okay, so if you want to be sure that the program is doing the same everywhere, using the same seed everywhere, then you need to fix the seed. Okay, If you just want to make sure that it's doing it inside the loop using the same seed, well, you need to use this other method here by just fixing the state. So that's pretty much what I had to say about fixing seed. But it's not something you have to think about when you do Monte Carlo. Is when are the random numbers changing? Okay, so at least when you're using random draws. If you're not using random draws, but you're using you're using Quadrature, you would never have to think about that. If there's other like pseudo-random draws like Halton and Sobol, they are not random at all. They're just the same every time. It's just a sequence. Of course, you can start the sequence different places, but it's the same sequence every time you call the computer. Okay. Now here you see the issue. So one issue here with the randomness is that if you look at it, some of these draws tend to be clumped together. We didn't get anything out here in this draw, right? So how do you make sure that you cover the entire distribution? And in finite samples, these draws could tend to be lumped together. You're unlucky to get some draws that just by chance we're looking we're in some funny place in the distribution. So that is what we can avoid with the pseudo random draws that are really like sequences that try to cover the integrals as good as possible, cover the distribution, put the unit on the unit interval as good as possible. But then at the same time, maintain the idea that as you move up to higher dimensions, you get uncorrelation across the different dimensions, so that you get finer and finer grids as you add more dimensions. So that's how do you do that? There's something called Halton draws and Sobol draws. And these are deterministic sequences. We're going to look at these. For this, you need chaos pi to get these. There's also something called antithetics. Think about if you have like a normal distribution, and say you take only one, you only take two draws, and say it's a standard normal distribution. This should be symmetric. Your two draws is like 1 and 1/2. Okay, now this is both to the right in that distribution. It doesn't have a zero mean, right? But that was just by chance. Maybe it's the next time you get them reverse signs, and on average, it will have zero mean. But then one way to reduce the variance here would be say, now what if I only took one draw? I only took one draw, and then I mirror that draw. So I suppose I get 1, then I also take -1. And then if you want to take 4 draws, well, you take 2 draws, say 1.5, and then you also get -1 and 1/2. Now you have ensured that the distribution is symmetric. Okay, for example, so you can do little tricks like that. Generally, it's called antithetics, and this chaos. These ideas are also implemented in chaos pi. You can do that. That's a way to reduce variance a lot. And a trivial way, if you do Monte Carlo in one dimension, you just take all the draws and then you say 1 minus those draws and you add those as well, and then you got your uniform draws that are more kind of equally spaced throughout the distribution. Okay, now all this is kind of pseudo-random. It's not really random, right? These Sobol draws and Halton draws. They also mean that they are not converging with the same parametric rate, the one over root n. In fact, actually, the rate of convergence depends on d. So we'll look at that a little bit later, but they have different convergence properties, although they do inherit some of the nice features in terms of at least ameliorating the cursor dimensionality. So here's a little function. I'm not going to go into so much into the details about what it's doing, mostly into the results it's producing this graph. Okay, so what we're doing here is that it is generating some draws on the unit hypercube, and then plotting them against, say, dimension 1 and 2, and doing that for various different ways of taking draws. You have the gender nodes that's required for the quadrature, for the 2-dimensional quadrature, using the product rule. You got some that's coming out of doing the sparse grids. You have the random numbers, you have the Halton draws, and you have the Sobol draws. Now you see here, if you do the plot draws, you see these random numbers, they are kind of, they're not systematically making sure that we cover the support of each of these two in a systematic way, whereas Halton draws, if you look at, they're kind of evenly spaced if you look at all these different dimensions, they're kind of evenly spaced. And the way these are generated is that, say, they're generated from using primes in each of the dimensions. So one prime, that would be like 2. So that would say, okay, the first draw, I take it in the middle. Okay, so I divide the interval into 2. And then the next draw, well, that's coming from some, say, taking the first interval, divide that into 2. That gives me 1 at 1.25. And then I continue to do it for the other interval at 0.75. And then I go forward and then take the first interval, divide that into 2, and so on and so forth. That's kind of a deterministic way of like filling out the support, right? You're sure that you put less and less distance between the points in a systematic way that covers the support. Okay. And then, of course, depending on the type, the prime, then you're going to divide this differently, and you're going to use different primes in different dimensions, and then you get some a little bit of uncorrelated shots. And snowball draws is done in a different way. I'm not going to talk about how that's done, but that's also in a systematic way. Okay, I'm going to show you more pictures of Holton draws, and why don't we try to have a little bit more draws. Here you see here they're kind of filling out the space, but here you got some holes over here in the random draws. So this is what the pseudo-random draws over here is kind of avoiding. Now look at the Gauss-Legendre quadrature. So let's take a little bit fewer here, just 5. Oh no, man, that was too many. Let's just do 5. Okay, that takes a little bit of time to do the sparse grid. And so what you see here is what you get here is like 5 by 5. There's 25 combinations of Gauss-Legendre nodes. These are the Gauss-Legendre nodes. It's just repeated, right? These are just the same for every value of the Gauss-Legendre node in dimension 2. Okay, so these are the ones for dimension 1, right? So and you see that doesn't change if I add another dimension. So it's still the same nodes. We just need all those combinations. Okay, now here's So whereas here that's not the case for Monte Carlo, right? For this value of my the draw in one dimension, I got this number, but then for some other value, the next one, well, that was close. The next one again, right? Then there was not even the other draws were not there. So it's kind of completely random. It's combinations of x1 and x2 that I draw, right? And these are independent. It's not like I'm doing the combinations of saying, okay, first I take some draws in one dimension, then I take some draws in another dimension, and then I do the combination like I'm doing it over here. That's not how you're drawing samples of random numbers, right? Then they would not be independent. Okay, so here's how it's implemented. Here's a code you find in the GitHub, and there's just different rules. We've implemented, or basically the rules, or you saw in the picture. And you can vary the number of draws, the number of dimensions. You can make a transformation. And we're going to use that later. We want to take these uniform draws and make them, for example, multivariate normal. We can do that, or we can print out some what the number of draws are, and then we can look at particular dimensions. So if you want to look at, say, the third and fifth dimension, how the draws would differ, then we can look at that. And then essentially this is calling chaos pi to figure out how to create those tensor products basis or these Cartesian grid for the Legendre nodes too, and taking all the random draws. So you'll have to look in the documentation. We have to move on. Already spent an hour talking about before getting to the point. So now we want to do we want to see how do we transform these to something that look like, for example, normal distribution. Okay, now we already talked about the inverse transformation sampling. Okay, this is exactly what we're going to do. The same thing, which is doing with a multidimensional case. So consider the case we want to do the normal distribution. Take a draw from the normal distribution with mean mu and variance covariance matrix sigma, and mu that's now a vector, right? That's d-dimensional vector of means for each of these random variables. And then there's going to be a variance covariance matrix that say something about what the variance covariance is between all these like d-dimensional vector of random variables. So and that we call capital sigma, just kind of emphasize it's like bigger than the little sigma. It's a matrix, right? So and then how do you then sample from that distribution? How do you do that? How do you get that epsilon? Now here's, we want to get like a d by n dimensional matrix of draws. and it's going to do, we're going to do it in the following way. So it's very much like what you did before. It's just, you know, taking the square root is a little bit different. Okay, and we want to work with matrix notation. So that's really just the difference. You're just applying your standard rules for the variance matrices and so on that you probably know already. But I'm just going to show you here. So first, we need to calculate, we need to find a matrix L that's kind of a little bit like, you know, our sigma before. We were scaling the whole thing with sigma to get it, you know, get the right variance, right? The little sigma, that was the standard deviation. You multiply with it, but now sigma is, that was like the square root of the variance, right? But now the variance matrix is a matrix and not a scalar. You just can't take the square root. So what we can do is we can solve this system of equations here. And there's multiple solutions to it. One of them is the matrix L that we'll call the that can be the lower triangle or Cholesky matrix. And you probably have seen that before in your linear algebra, but if you forgot, it's really just a matrix that you multiply it to itself that gives sigma. Okay, and you get it right out of Python just by writing one line of code. I probably yeah, we do it like here. It's just in the lin-alg Cholesky function, and you just get your L. So once you have that, you're ready to like transform the independent rate of normally distributed variables so that you can get a variance covariance matrix sigma. Okay, so what you do is you generate a matrix U with independent IID draws, right? Those are from the uniform distribution. Now we know how to transform each of them to independent normal distribution by just putting them into the inverse CDF of the standard normal. So we can do that with all of them. Now eta here is now standard normal distributed. Okay, now it still had the variance, which is 1 for all the random numbers. That's not what we want, right? And it also still has a mean of 0. So we can easily add the means, change the mean by adding the means. So that's what we do. And then we multiply with our new, square root of the variance or our Cholesky factor to this vector of independent random normals. And then you got it. You got your normally distributed random matrix that comes from this distribution. Okay, so these are the steps that you follow. And then we can verify the properties of it. You know, obviously, if it's normal, if each of these draws here are normally distributed, then once you start to add them together, they're going to be normally distributed as well. And so any linear transformation of non-linear of normally distributed variables is obviously going to be normal. So that's good. And then let's look at the means. If you take the mean of what we have here, well, this is just a scalar. You can put that outside the expectation operator. This is also, or it's not a scalar. It's a matrix, but it's fixed. It's non-random. This is also non-random. It's just the parameters, right? You put that outside the expectation operator, and then you're left with the expectation of eta, which is coming from the normal distribution with mean 0. So that is 0, and then you're left with mu. So this guy here, that works. And then the variance covariance matrix. How do you calculate that? Well, here's a variance formula for a vector of random variables. And so we just put that right in here. This goes outside. These are just parameters. This variance here, what was that? Well, we generated eta so that variance was 1. So this is just it's 1 for all the random variables. It's just the identity matrix of 1s. So that whatever side you multiply that on, it's going to disappear. And then you have to be left with L by times L prime, which is exactly how we generated it, so that it would multiply to itself. It gets the variance covariance matrix. So it seems to work. So, well, before we can kind of move on with this, we need a variance covariance matrix. So here's a little routine that builds one that has constant variance across the different random numbers and or the random variables, and a constant pairwise correlation between two random variables. This only works really for a positive correlation. Otherwise, you get into the messes of figuring out, okay, this is negative correlated with that one. That has to be this one over here has to be positive correlated. You know, that's kind of a mess. So here's just an easy way to do the positive constant positive correlation matrix, something like this. Here's a correlation matrix where you got like a correlation of 0.5, and that's what you get when you call this function here with the input 0.5 for the the constant correlation. Okay, let's, what happened there? I tried to zoom in, but that was not a good idea. Okay, anyway, so, so, you know, you see here, you can change it, and then suddenly the correlation becomes bigger, and then the implied variance covariance matrix is this one here, and you see there's covariances, they're different from 0, and you can control the overall variance by controlling this guy here. If there's no correlation between them, just so you can see you got zeros at the off diagonal. That's your variance covariance matrix. This is what this is producing. Now it's also doing the Cholesky composition, so I can print it out and show you, but really the main thing is it's producing sigma. And now what you can see here is this is Cholesky decomposition. And so let's take an example here where we have like a two-dimensional, and then sigma that is well, so let's take it to the square root. No, let's whatever, let's to do one. Okay, never mind. Okay, what you see here is this guy here in the case where you have the independent random draws is really the square root of this guy here, right? I mean, you take this number, multiply it to itself, you get 0.33. You could do the math, but that's what it's doing. Once you start to have correlation, well, it only applies for the first number, but then you get like different variances because they have to add up and get that correlation matrix. Anyway, so these are the type of stuff you get. You can get like different types of correlation matrices in within these bounds, and we're going to use that for running our simulations or further down the line. Okay, so that's basically the idea. So let's move on and try to see if we can transform some random draws. So here's I mean, it's as simple as this. The transformation itself is really just one line of code, right? Or two lines. First, you calculate the linear of the lower triangle transition matrix of the variance covariance matrix. And then you add the vector of means, and then you multiply that Cholesky matrix with your standard normal draws, which are the the inverse, or you get by taking the inverse of the standard normal and apply it to these uniform random numbers. So this transforms uniform random numbers to normally distributed random numbers with mean mu and variance covariance matrix sigma. Okay, so that's what this is doing. So why don't we do it? So here we take 3 dimensions, 1,000 draws, create our variance covariance matrix with no correlation in this case, simulate our random number draws, and then put them into our inverse transform with these parameters. Okay, and then let's plot the results. And you see here, now what I'm doing here at the end is I'm calculating actually the covariance matrix of the simulated draws. And that correlation matrix or covariance matrix should actually add up with exactly with sigma, right? Which is what we print out here. So this variance covariance matrix has a draws of 0.33 along a whole long way along the diagonal. So that's a theoretical one. Did we find that here in the simulated data? Well, not quite, but almost, right? So what if we just increase the number of draws? Do we get something like this? Well, 0.33 on the diagonal looks more like it, right? So so it seems to be working, and of course that's kind of reassuring. Do we get correlation across the different random variables? If we say, put C to 0.99, well, you saw that correlation matrix that implies that the covariance matrix has covariances that are very close to the variances. The Cholesky matrix we calculate, and then you also find that exactly the same pattern in the simulated data. So it seems like it's kind of it's kind of working, right? So let's move on and see if we can basically take the uniform random draws, not only in this in picture, and make some pictures of them, and see if we can transform those uniform random draws so we get in one dimension, and see if when you apply that transformation rule, which we're doing in the lower set of graphs, and we start to see something that looks like correlated normally distributed variables And what is the mean supposed to be here? It's supposed to be 1. Is that true? Well, that's certainly transformed so that the mean is around 1. What is the variance covariance matrix? Does it imply a positive correlation between these two variables? Well, the correlation is 0.9. You see a very tight linear relationship between the two draws. So, and it does look like, the scatter plot, you will get a normal distribution with more and more mass in the middle and less that you go out, and there's like a very low probability of getting anything up here. Okay, so this is transforming the random draws. You get this. You transform the Halton draws. It also get this, but it's just like the cloud or the galaxy of draws here that just looks much more clean and nice and well behaved. And same with the Halton draws. Here you got the gender sparse and the gender quadrature. It doesn't look like a normal distribution, but remember here, these are different, right? These are different because here, the weights are the same on all the different draws, whereas over here, we're calculating a weighted sum. So the weights here are very different from the weights right here in the center where the mean is, right? It's going to be much higher weight, and that's how, we have a combination of both nodes and weights. Okay, so that's pretty cool. Now this was actually generated for a 5th dimensional example. I'm just plotting dimension 1 and 2 here. Okay, so what I'm doing here is I'm taking the number of draws, that's 5 to the power of d. And I'm doing that to make sure that I get the same number of draws for the random draws and super random draws as I do for the quadrature approximation in the product rule. Okay, so you see here for the gender product rule, I get 3,125 nodes in total, but that is combinations of 5 nodes in each dimensions in each of the 5 dimensions. So it's like 5 to the power of 5, right? That's 31 or 25. And so, but I don't see as many dots as I do over here. And why do you think that's the case? Well, maybe you want to pause and ponder about how and stop and think about that. But if you can also just get my explanation, here it is. How do these were generated? How? Well, these were generated in a way we essentially took the Legendre nodes for each of the different combinations. So we only have, like, for dimension 5, we only have 5 combinations, and we just combined them and took all the like the Cartesian product across all these 5 different dimensions. So you see here, there's no variation in whatever that node is for dimension 1, irrespectively of what all the other dimensions are. And here you see dimension 2 clearly, right? They're all on top of each other. Whereas that's not at all the case for the random draws. They're going to be different across all the different situations, which means you kind of fill out the box more and more as you get more and more variables, right? Because when you look at the pairwise correlation between 2, it doesn't really matter what all the other ones are, right? And so that's kind of the power of Monte Carlo, filling out the box and using getting more and more coverage on the support of the random variables as you add more and more dimensions. So that's how you see it. I mean, you can try out things here. If you have like 10 dimensions and only do 2, right? Then the picture is going to be very clear. So here's like a 10-dimensional integral. I only have 2 quadrature points for each of these. Whereas I have like 1,000 draws. I have 1,000 quadrature points. I can have 1,000 combinations, or 10, 21, but I'm not really filling out the square, right? So that's very clear, whereas you do it much better with these other methods, okay? Okay, so now that was how it kind of fills out the dimensions and fills out the square in high dimensions, okay? So why don't we try to see if we can do a little bit of Gauss Legendre using chaos pi. So let's go back and do quadrature first. And so we want to try to see if we can solve this integral. Now we know from our theory, from the one-dimensional, that's applying just extending to the multidimensional, that we should be able to really nail this integral if we just have enough nodes. Okay, in particular, if m was equal to 2 times n, where n is the number of nodes, minus 1. So m is equal to 2n minus 1. If that's the case, you got 0 approximation error. Okay. And that applies also then in high dimensions. So that's what we're trying to illustrate here. So that's why we try to put, we take so many draws here. And what is M here? M, where did we set M? Did we set M anywhere? M is 7. Okay, M is 7. Okay, and let's look at the results we already got here. So D, that's a 6-dimensional integral we're looking at. That implies 405, 55 Legendre nodes because we are using 4 in each of the dimensions. And then the order here is 3. Okay. So what is a quadrature? It really nails it. The true value is 31. I mean, we can easily do that in integral, right? That's high school math, computing the integral of an integral of a of a polynomial like this, right? And so I've typed in here where the true value is. It's really, you just evaluate them in the endpoints. The antiderivative is just raising the exponent by 1 and then divide 1 plus the exponent, and then you're kind of there. So that's trivial to really calculate the analytical solution to that integral. And so that's a number that's plotting over here. And then what am I doing here? I think we are doing it both based on the tensor product grid. So this is what you get here. That's how many grid points. But you get exactly the same with much fewer points in the Smolyak grid, and get exactly the same order of approximation. Now, and you nail that right, because the order is that is 3. So 3 times 2, that is 6. Or 3 plus 1, that's, you know, that's also a constant, right? So 3 plus 1, that's 4, minus times 2, that's 8, minus 1, that's 7, and that's exactly what we are trying to approximate, a polynomial of degree 7. So if we were to increase this to 8, well, then you would start to get approximation error, right? And of course, it's kind of in the ballpark, but the approximation error is there. Okay, so but what I want to illustrate here with is that the sparse grids, it doesn't use all these different combinations, gets its exact same approximation of the integral and really nails it only with 455 points instead of the full tensor product or the full Cartesian product that implies 4,096 points instead. Okay, so really the Smolyak algorithm is ameliorating that cursor dimensionality. Okay, and yeah, so that's it. You know, yeah, we had 4 points in each dimension. Remember, 4 times 2, that's 8, minus 1. That's the rule. If you can, if the function of interest is a polynomial degree 2n minus 1, we're going to have no approximation error. It was degree 7 polynomial, so it was supposed to nail in that case. And that result applies to the higher dimensions as well. Okay, so let's move on and go a little bit back to the Monte Carlo. Now, I was kind of recommending that you reuse these Halton draws and Sobol draws to reduce variance and avoid these awkward situations where you have some draws just accidentally being lumped together, biasing the result, or at least giving a higher variance to the result. Now, see, problem is we really want these to be uncorrelated across the different dimensions. And so here, what I'm doing is I'm plotting, you can change that here, what dimensions you're applying. I'm plotting the last 2 dimensions instead of just the first 2 ones, okay? And so if I were to look at say, you know, 2-dimensional problem, last 2 dimensions, that would be 1 and 2. They're clearly, you know, seems like something that is, you know, independent across the 2 dimensions. Oh man, is there a way to escape from this? No, yeah, let's see if it meets. Anyway, that's a killer. Okay, I don't want to go out and change it. Anyways, you see here that that there doesn't seem to be like any dependence between the 2 dimensions. But if you were to go to the 2nd dimension, or the 3rd dimension, well, what happens? Well, it still looks good. 5 still looks good. In dimension 10 and 9, you start to see patterns where there's this correlation across the alternatives or across the random variables, you go to 11 and 10, it starts to also get, these funny patterns. And that funny patterns actually translate in once you start to transform the draws. They suddenly don't really look like bivariate normal distributed draws. And you get these weird patterns. You get further up, it gets even worse. And you see here, this certainly doesn't look like it's something that's independent normal or bivariate normal. This does not at all look independent. You go further up to dimension 101, well, they're almost like perfectly correlated, the Halton draws. Whereas look at what happened with the Sobol draws. They seem like to be happy. Still, even when you go to dimension like 200, Sobol draws are, it's not perfect, but it's definitely getting the same, much better coverage, right? You don't have this perfect correlation between the draws that would render these Halton draws completely useless. Some people use Halton draws for the lower dimensions, or they shuffle the Halton draws to make them somehow more random. But really, if you want to, and this is kind of illustrating why when you go to higher dimensions, if you really want to break the curse of dimensionality, well, you got to get the random draws, or if you want to stay in moderate size dimensions, well, Sobol draws is good if you're working with something like a 100 or 200 dimensional on school. You don't want to use Halton draws for sure, at least not the clean ones, right? So that's kind of that's what I have to say about this. You have to be careful using these methods, know what you guys are doing, right? So let's kickstart the MC, if you will, right? So it's like, you want to solve like 1,000-dimensional integral, and we have one where we know what the solution is. Now, even doing the Smolyak algorithm with the quadrature is not going to be feasible for this one here, okay? And if M is just anything different from 0, or maybe not 0, but if M is a little bit higher, so you need more than two quadrature points or more. Like if it's 3 or more, then just forget about solving a 1,000-dimensional integral, right? Because 2 to the power of 1,000, it's already infeasible. You can't do that. But with Monte Carlo, we can just completely nail that guy. So here's how we do it. We just take, we take like a 1,000-dimensional integral. We take 1,000 draws for each of these 1,000 random variables. Okay, so now we need a million numbers, but it's not like fantasillions of numbers. We need just a million numbers. Okay, here's a function of interest we want to integrate. That is, this x to the power of m, and we take the mean of it across all the different dimensions. And then we want to try random Halton and Sobol draws. Okay, so let's do that. And actually, it's already done. And why don't we illustrate? It doesn't take that much time. You see, like this is solving a 1,000-dimensional integral, and the true value is 10.5. And I would say this is kind of in the ballpark, right? And here for the random draws, we get a bias, or we can calculate the bias because we know what true value is. But we get a standard error of 0.02, which is kind of reasonable, good standard error for solving a very complicated problem. And then these numbers do not, the standard errors do not apply once you go to the pseudo random draws, but still get some idea about the approximate how much variance there is. But of course, these draws need to be random for the number random number for the central limit theorem to apply in the law of large numbers. So that's in principle not really a standard error. But look at the Halton draws. You start to get bias here, right? And that bias, that's because of these problems in the higher dimensions. That bias does not appear to be a problem for the Sobol draws. In fact, random draws was actually better, right? So why are we even thinking about doing these other sequences? Well, that's because not all integrals are 1,000-dimensional. If you took only like a 10-dimensional integral and look at the bias, it's much smaller for the Sobol draws and the Halton draws. And so for moderately sized problems, you want to use these instead, and the variance actually becomes smaller. Look at the 2-dimensional case, right? You got only with 1,000 draws, you you get better performance with in the two-dimensional case only with the Halton draws and the Sobol draws in the lower dimensional integrals, because you're kind of in systematic way filling out the box. Okay, so but you know, nothing really beats random draws once you go to like 10,000, right? Here's 10,000. Okay, so I can't do the Sobol draws because they only allow up to 1,100 dimensions, which is usually good enough for me. But here's like a 10,000 dimensional integral, and we're using you know 1,000 draws in each of the for each of these 10,000 random variables, and what are we getting? Pretty low bias. Okay, so that is really, you know, that's encouraging. Okay, so let's put it back to this, like so it fits with the header here, like 1,000 dimensional integral. We can easily do that. Of course, this was a simple integral, so the performance and the size of the standard errors, that inherently depends on the function that we're trying to nail. Okay, that depends on the function we're trying to nail. Okay. So why don't we do some more comparisons, and you know, and you got this far, you pretty much know what to do, okay, to do the Monte Carlo. So I'm just going to do a little bit more of test problems. So here's a test problem where we'll calculate the integral of the sum of a normal distributed variables, or a function of a normal distributed variables. And so this is our function, which our function is just a sum. It's another test problem where it's a product of log normally distributed variables. So our function is the product of all these exponentials of x, which is really the same as the exponential of the sums of x. And so why I'm testing these problems? Well, because I know what the answer is. You know, I know what the mean of the sum of a bunch of random number, a bunch of normally distributed variables is just the sum of all the means. So I know what the variance is and so on. So I mean, these are problems we can handle. And so here we're doing a little bit of test. Here it's with I'm doing it for test 2 for the log normal distribution. You can flip it and write 2, and then this is for test 1. And so here's what you get. We do it for various different methods here for the. So here we do for sparse grid for the tensor product. We do it for the random draws, for the Halton and the Sobol draws. And what you see here, it's got the true value in the quadrature. They can, with 5 points in each dimension of the state space, they get an approximation error of this order. And actually, with Monte Carlo, in the same number of draws, you get a lower error. Okay. That's not the case if we were to do a two-dimensional case, my guess would be. Then Monte Carlo gets actually a pretty large standard error, right? Because now we have much fewer draws. We only use 25 draws, okay? And that would, you only need like 25 puncture points, the combination of 5 to the power of 2 to get the same, to have this, you know, same computational complexity in some sense. And yet the approximation error in that case is just much smaller, right? If you were to do test problem 1, this should really nail it, right? So if you write 2, this should really nail it with quadrature. Yeah, there's no bias at all. So that's why I'm looking at test problem 2, where it's a function of the exponential of the normal distribution. So the product of these log normals, this problem here, that's the problem we're looking at. It's just a little bit harder problem. This we should be able to nail pretty easily. Okay, so yeah, you know, this is just, you know, try it out, figure out, you get a feeling of what the pros and cons of the different methods is by moving around, for example, the dimensions. Like if you want a 10-dimensional case, for example, let's we can only allow for, say, two grid points in each dimension if you want to do quadrature. Otherwise, you know, the number of nodes just becomes a little bit too big for an illustration. And see here, you know, it's really off with the quadrature, whereas if here your standard errors are much lower, and you kind of seem to nail it. Again, we see the same pattern with the Halton draws. We've got high dimensions. This dependency across the different dimensions really actually is a problem for us. Whereas the Sobol draws seem to be able to take the best from two worlds, really work well in high dimensions and also work well in the lower dimensions. Okay, so if you're kind of in the area in between, you don't know if you're really need to leverage the randomness and do the for your problem in a high-dimensional problem, then actual Sobold draw can be a very good compromise. And these can actually be computed in parallel, even though they are sequences. It's another computational advantage of the Sobold draws compared to Halton sequences that are inherently sequential to compute. Anyway, I think I'm not sure about Halton draws, but I know Sobold draws can be computed in parallel. Okay, so back to the properties. I just want to also remind you, we got the asymptotic normality, we got the rate of convergence that's independent on the number of dimensions. So we want to just illustrate that a little bit more. So now we're going to do something called Monte Carlo squared. We're going to make a Monte Carlo experiment where we investigate the properties of our Monte Carlo approximation of the integral. So it's like a Monte Carlo of a Monte Carlo, okay? So, keep tight. Essentially, I'm just doing what we did before, and you can look at the code, right? I'm solving this integral here. So there's a function that calculates that integral using Monte Carlo, and you can have all these different rules. But then I'm doing that for a bunch of different Monte Carlo samples, okay? So repeating that exercise, I'm saving the results, okay? So I'm saving the Monte Carlo estimates and the standard errors, and then we want to look at those, okay? So, and then there can be some output, and sometimes we want to look at that as well. So this is what you get out of it. So we're doing this for first the test problem 1 and 2, and let's just actually just comment this guy out here, so we only see what we're looking at first for test problem 1. Okay, so what we're doing here is now we're taking 1,000. We're looking at a situation where we're using 1,000 draws to solve a 5-dimensional integral that has this variance covariance matrix with no correlation across different random variables. You can change that if you want. As this mean, and I'm using this mean because I want to keep, as I increase the number of dimensions, I want to keep the mean constant at 1, okay? Just to not make the problem explode if you work with a very high dimensional problem. And then it plots the distribution of our Monte Carlo estimates of the Monte Carlo integral, okay? You see, you get different numbers depending on what it is. But what is those numbers? I mean, the true value is supposed to be 1 in this case. Okay, that's the mean of the sum of d normal distributed variables that each of them has mean equal to 1 over d. Okay, so that's supposed to be 1. That's the true value, and it's also printed here and here. And then you got all these different estimates. It's a standard deviation, and this looks like to be something. What is the standard deviation? Probably something around 0.4 or 3 or something, which is also what we print out here. Well, that's what we have. That's a standard deviation in this distribution. That's 0.3. But what about if I took all the standard errors and took, because that's an estimate of the standard deviation in this distribution, looked at that, took the average, that's what I have here, right? So then I take the expectation of the standard errors. That's, if these two are alike, this says, okay, our theory is very good. Our standard error is actually a very good estimate of the standard deviation in that distribution. And so it is a good measure of how precise our Monte Carlo estimate is. And it does look like a normal. I didn't do the test, but this means like 2 times the standard deviation on either side. That's a very good confidence interval with 95% probability confidence interval. You got the average estimate. You got the average of the bias being 0. So that all looks good. And you can do it for the test problem too. So that's, I mean, it's doing graph in this line. So I'm just going to comment out the other one so we don't have to look at two at a time. So now it's doing for test problem number 2. It's doing a little bit of, many times because we're doing essentially to really nail that distribution. I'm doing the Monte Carlo with 1,000 draws of 5,000 times. Okay, and it does look like a normal distribution here. It apparently there's a little bit harder to capture it because now the test problem was a little bit more difficult. You see a little bit more bias than we had before. The standard error and the standard deviation is still pretty close. And I would say if you were to increase this with a bigger number, actually what you would probably see, what theory will tell you would see was that this distribution is actually a normal distribution. So I mean, I really encourage you to try to run different experiments to get some good intuition for what is going on. Like, why don't we, what more can we do? Well, we could we could try to increase the number of observations. We could try to other types of draws. Well, but if you do the Halton draws, let's try to actually do the Halton draws. So where would we need to? That is here. I think this one has the input rule. Okay, it's a little bit ridiculous to give it the rule. But I'll just do it for an illustration because you'll never do that. If you put the rule equal to say Sobol, you're not gonna see a distribution, right? Because these draws are the same every time you take a sequence of Sobol draws. You're just gonna get the same number. Okay, so in fact, there's no reason to take 5,000, do it 5,000 times, but just for the sake of illustration, I'm gonna do it anyway. Okay, Sobol draws takes a little bit longer time to compute. So you have to be a little bit more patient. Maybe, yeah, okay. And you see, but you don't have to do it 5,000 times because you get the same result every time. Okay, so this is kind of illustrating that randomness is coming from the randomness. You get the same answer every time. So if they're not random, you're not going to get a random result. Okay, I'm just going to put it back to the default, and just to recreate this situation, I'm just going to run this, and then we just move on and look at the rates of conversions. Now that was the actual distribution that it converged to, but how fast does it converge to these distributions? We alluded to that would be the rate of 1 over the square root of n. Okay, now let's look at that. That is pretty awesome, right? So it's not even a function of the dimension if you're using Monte Carlo. You can see with the I said in the beginning that the pseudo Monte Carlo draws, it will converge at the rate of log n to the power of d divided by n. But so what does that mean? Try to wrap your head around how these functions are changing as n change for different values of d. Well, you look at them and you see that in order for this rate here for the pseudo-random draws to be smaller than the parametric rate, and the dimension d needs to be small and n needs to be large. Okay, and so it's easy. A graph is 1,000 words. Here you got the rate of convergence for the random draws, or the convergence, how the error disappears. For the random draws, it's a blue one, and then for the pseudo-random that kind of goes lower here. I make them so that they meet in the same point here. And no, I don't. I just plot the fungus. And then you see here in lower dimensions, it's almost always the case that the pseudo-random is converging faster in the rate of convergence is faster. But once you move to higher dimensions, like fifth dimension, then you really need like a lot more draws to get that rate of convergence to be lower for the pseudo-random draws. Okay, and if d is equal to 10, well, then 10 to the power of 15. I'm not gonna have so many draws on my computer, so that's just impractical, and it may be better in these cases to work with just the ordinary random draws, just like we saw in the experiments we were running before. Okay, so but let's just see this last slide. Does this central limit theorem result apply and can somehow illustrate, okay, for the random numbers? Now what I'm doing here is I am doing a Monte Carlo where I'm varying the sample size. Well, maybe you can't see it, but it does say n here. So you get the sample size here on the x-axis in all these different graphs. The first one is the bias. And you have to look at basically what we look at here, the bias, that is the bias if you were doing like a Monte Carlo squared, again with lots of replications, right? Is actually supposed to be 0 for any sample size, right? It's asymptotically unbiased. I know the result only holds asymptotically, but it's going to be unbiased, asymptotically unbiased, and so this is going to circle around 0, which is the red line, for any value of n. And you look at the variances here. They're quite small. So what do we have? 0.1 here. That's pretty. It's actually at the order of the variance. We have a very small sample. And what is that variance coming from? Actually, we can make that variance smaller simply just by increasing the number of Monte Carlo replication in our Monte Carlo study of the Monte Carlo estimator. So we increase that, say, to 50, then that number is supposed to be smaller here. Okay, so it didn't have, right, because we're converging at root n. But this noise here is not coming due to finite sample bias of the Monte Carlo. It is due to a noise in the fact that we are doing only like 50 Monte Carlo replications in our Monte Carlo study of the Monte Carlo approximation of the integral. Okay. Now let's look at how that variance on this, or the standard error, is decreasing in the sample size. That's the next graph. Doesn't that look like the square root? Well, doesn't it look like it's converging at the rate of the square root? So what if I were taking and multiply 1 over the square root? If I multiply this number here by the square root of this number here, like the square root of n, our theory tells us variance should be constant. Okay, it should be constant. And this is what we're doing over here. And here you got 1, and here you got 0.98. It's virtually constant. Okay, it's virtually constant. That's really confirming we have the root n consistency, or the root n convergence. You take the standard deviation, multiply it by root n, and then you get a constant. Okay, that is exactly what we had in our theorem, right? So that is what we had right here. Where was it, right? If you take this number here, multiply with square root of n, you get sigma, that constant variance. Okay, so that's really powerful. Now we're almost there. This is the last slide, last figure. So what we are doing here is essentially just taking the square. This is just another way to show the same thing. I'm taking the standard error and printing on a log scale together with 1 over the square root of n, just to see, okay, do they actually follow this? I mean, you have on the x-axis, you have n. Again, it's just like a log scale instead, and you clearly see that this root n consistency, right? That's just another way to show the same as we're doing right here. It's just another scale. So the last thing I want to do is I want to compare with some of the pseudo random draws. So now I'm going to change this to 1 because there's no reason to do Monte Carlo sampling and repeat that a lot of times with the same numbers. And if you're doing Sobol, for example, you're going to get the same sequence every time. So no reason to do that so many times. Let's try to see, how does it convergence? Do you still get root n consistency? Well, you were not, you shouldn't get root n consistency. You should get a convergence rate that depends on first of all, it depends on the dimension, and also doesn't follow the square root. And this is why, the blue line, that would be exact root n consistency. But you see here, it converges slower. It converges slower here in the beginning, and then you get to something that is less than root n consistent, right? So, actually converges faster. It converges faster. Okay, so it's steeper than the square root of n. You can see here, when you multiply with the square root of n, it would have been constant otherwise, right? It's still unbiased. And you see here, so these have just different rates of convergence, and it doesn't have that constant variance, meaning that you can't actually really apply the law of large numbers and get the standard errors and so on. So these, in some sense, these are kind of invalid, right? But that's all I have today. And there's some, lots of further things to learn out there. And next week, it's going to be about functional approximation. We'll look forward to that. So yeah, thanks for listening, and bye-bye.